First of all, thanks Kalev and thanks Sandor. So great to be here. I can't believe I'm standing here today. So we've been working with Kalev for almost a year now. So it's been really nice. But first of all, the team that has been conducting an evaluation. Project owned by Martti Jeltsov, Technical Director of Fermi. Excellent colleagues from Vattenfall, Markus Eriksson being here, leading that team. And we've been doing good stuff here for 10 workshops, also meetings with the supplier. We see some supplier representatives there, for example, lead engineer or chief engineer Krister there from GE and some other faces that have become familiar here. And a good team working soon, actually, for half a year to understand the plant. So I'm going to tell about it. My name is Timo Okkonen. I've done 35 years in nuclear branch, leading regulatory affairs, leading research, leading actually quite heavy, big projects technically. For example, INC modernization. I've been leading inspection businesses on component level for more than a decade, and lately also leading a power company in a very tough project, getting it going after difficult years. And what I enjoy mostly working with Fermi is that we are doing some new stuff, and we can influence things on the upstream, try to do things good from the beginning. And it's a pleasure to advise, coach Kalev's team. I'm going to take first everybody out from the nuclear scene. We're going to go to the woods. Why is that? Here is a picture from my summer cottage. We were building a hut, and we had a carpenter, and we still have Jykke. You can see on the right-hand side. Jykke really likes coffee. Some might say, why do you take a carpenter who likes coffee so much? Well, he does, and he's excellent. So coffee is so important to him, so I came with an idea that let's build a safety strategy for the coffee. It's called defense in depth in nuclear. So how do we make sure that it will absolutely never run out? Because otherwise we don't get the hut ready. So let's start with the normal operation. Jykke likes to bring his own coffee. He's pouring things, he's doing things there and so on, and he drinks it from his own thermos bottle. Perhaps once per 10 days it runs out. What do we do then? Well, we as a family, we prepare some coffee. We are mostly there, at least 9 out of 10 days during summertime we are there. So we make coffee. Of course, then we are dependent on our own coffee machine, in addition to us being there. And we are also dependent on the electric grid. So some of them might actually fail. Let's say 1 out of 10 days, Jykke runs out of coffee, and then with a factor of 10 lower, 1 out of 100 days, we are actually perhaps not there, or the grid is out. Well, grid is pretty good in Finland. Hope it stays like that. Then we need protection. That's really the safety. Well, here I propose that we buy 2 battery-driven coffee machines. So that's an example. We will decrease the probability of losing coffee with one more factor of 100 or even 1,000. So we are getting down to 10,000 days or 100,000 days. We are getting safer, we are getting better. Well, somebody might say these are standby systems, we don't use them normally. And it might accidentally be such a situation we try to start them up, they don't work. Even if we have actually 1 extra there to fulfill so-called single failure criteria. For that we need a backup. We might need an aggregate to load those batteries if the grid has been gone for a long time, or we might actually have a diverse battery-driven coffee machine. Okay, everybody would like to have a passive system here. Probably X300 is not for this mission, but I call X300 easier for me to pronounce. Sorry, GE Hitachi, so I BWRX-300. So that's, we bring with a factor of 10 more. In this case, we have a very good situation because even if these would actually not work, our carpenter could drive to Mikkeli, to the town, and have his coffee there. So we come down to once per million days, we lose the coffee. And if even the coffee was not available in the market, we might shift to tea, actually. Well, Jykke wouldn't like it. But this is defensive. This is the way we build safety, actually, in nuclear power plants. In reactor circumstances, we don't talk about days, we talk about years. So we're basically driving the modern reactors so that any bad situation would happen much less than even once per million years. Design is good because this even allows some human errors. We check everything very carefully all the time so that they don't really influence any of these devices, but if they do, we always have the next level of defense. How do we do our evaluation for a reactor? In the middle, you see this defense depth. We are studying different important functions of the plant and checking out, do we have these defense lines there? And are they independent of each other? So that if one fails, the other ones will be functioning. You see barriers. We are doing this because we try to protect these fuel and reactor circuit and containment so no radioactive things come out of the plant. For that, we need safety analysis and risk analysis. So we check out a little bit how those analyses are done. And on the left-hand side, you see our ultimate target of practically eliminating a situation where any radioactivity cuts out of the plant. Would be not good for the environment, not for people, not to be able to use that land in long term, as we have seen in accidents in the history. And throughout these 5-6 decades of power production, we have learned a lot, and that's why we do things in this way. The old world was more safety, non-safety. Nowadays, we have actually 5 or 4 defense lines. On the right-hand side, you see failures. Sometimes devil is in the detail, because some special failure modes in one line might affect the next one. As I said, for example, the grid or some dependency could influence both the normal coffee thing or the backup thing. That's why we study them. And on the right-hand side, of course, there are very good strategies here by GE Hitachi of quality assuring those deliveries in accordance with the importance of different parts of the plant. So this is the way we evaluate with our team. And next I'm going to run through the reactor in a simplistic manner. How do we actually study the reactor? Reactors are more simple, but often we make safety quite complex. And I believe we have to actually try to make even that quite simple, because in that way we focus on essential things. Let's start going through that. So this is a fast course from our team to everybody on X300 safety features. And first there is reactivity and shutdown. In order to handle any situation, you first have to shut down the chain reaction. Then you have to make sure that the reactor pressure doesn't go over because some heat is being generated all the time. Then you also have to have a bit midterm actually cool the reactor, that you don't actually by steam or leakage get out actually the water, so you are still cooling the reactor. Critical break isolation means that you may have some isolation places where it's very critical to isolate, shut those places if a pipeline breaks, for example. And in this reactor, there is a very innovative solution for that. Radioactivity confinement means that then we also check out that these barriers will work. So I will run through these 5. I'm not going to go through all the details, but I try to run these things and form an architectural view of the plant. What kind of features are there to make it basically practically eliminated that we end up in a disaster? First, normal things. You can see things like rods. You are using control rods to steer the nuclear power. The reactivity, of course, you have other control systems like feed water control as well. BOP stands for balance of plant, which means that the pressure is being taken care of by the turbine side, not the reactor in itself. Cooling also, we get the heat to the sea or to the air or to the turbine condenser. You see critical break isolation is not there, but the quality assurance is so high that it's very unlikely that we have substantial defects in those pipelines or the barriers, really the physical barriers. And then the radioactivity is predominantly, basically almost completely kept inside the fuel. That's what we call normal operations. For Jykke, that was drinking coffee from the thermos bottle. Here, this is it. And very important for any team, and especially for a new company like Fermi, for the team to learn. And that's why I'm here to really coach the team, that we together learn how this really works out. You don't really learn the plant by reading regulations. Sorry to disappoint if somebody believes that. You actually read it by actually learning how it works and talking with the designers. And we have excellent designers from GE Hitachi. We've been able to ask questions. Some of these might go wrong. It might be any of them. But for example, it might be that there is something problem with the plant on the turbine side. You see, anticipatory means that, for example, you could see very early that something is going wrong on the turbine side. And that signal comes in, and you may utilize that to actually try to re-steer things. You see on the critical break isolation, before we have a break, you need to have a defect in the material, and then you need to miss it by inspecting. We are regularly inspecting the plant, and the more critical places, we are inspecting more regularly, more frequently. And then we are monitoring the plant. Sometimes in a new plant, it may happen that in the first cycle, you, for example, get some fuel leakages, and you are monitoring that. And then you decide what to do about it. Whether you shut down the plant or whether you can live with that minor leakage. And even in operating plants, we sometimes have leakages from the fuel. Very minor, but still important. And of course, the plant is designed to actually filter out or clean those leakages. This is the preventive line. Then we come to something that is called really safety, some standby systems. And for that, the X300 has quite much passive features. For the reactor shutdown, it means that we actually see that we need to shut down the reactor, and we pneumatically cause a hydraulic insertion of the control rods. So we open, some valves are open, and the rods go in, and they shut down the nuclear reaction. Then we have passive features, so-called isolation condenser, which nicely regulates the pressure, but also provides the cooling of the reactor. After opening valves, it passively does that. Critical break isolation, there are particular isolation solutions here, which isolate, for example, big lines directly close to the reactor vessel, so that actually you are very highly unlikely, if not completely ruled out, that you would actually have any bigger leakages from the reactor, which is a very unique feature, which is part of the reasons why this reactor is so much simplified from the predecessors. Reactor circuit, when you are cooling it by the isolation condenser, you are not getting steam or anything out from the reactor, which means that if there was some little leakage there, it would be contained inside the reactor circuit. Now we are on the protection. We use the color black there, like the black belt. This is the part of the plant that you typically try to make sure, absolutely sure, and this is where the licensing is mostly focused. And this is an area where you try to be as simple as possible, often also as passive as possible, because to really show that this is not complex. And you also make sure that this functions for a long time without any human intervention. In general, this defense in depth also prevents human errors of having a big impact. But it also makes it such that the operators are trained to do a lot for the normal operation, but they are not forced to do anything when really needed in an accident situation. They are actually often trained absolutely not to do anything, because in some accidents that we have had in the past, Kalle was asking about those in the break, it's been often so that some mistakes are done. In this black side, you actually believe very much in automation. And you try not to intervene, because otherwise you might actually do a mistake. So even those things are part of this defense in depth strategy, that how do you see the role of the operator? Then if that would work, even that black, which is the most best black belt area, would not work out, you often have some backups. For the control rods, you have a motor. After you have done the hydraulic scram, even the motors are slowly pushing the control rods in. So they are backup. You see passive with an asterisk there. It means that there are two different valve types that actually activate the passive system. Because the other part of the structure is just a structure. So there are two valves, one red valve, one blue valve, for example. Then we are studying this little bit. This is very much language that we are using here. GE doesn't use exactly this language. We try to form our view, and our team is quite experienced in the boiling water reactors because Sweden and Finland have them. Myself, for example, I've been a lead engineer on a boiling water reactors and even on a full high-NC modernization. So we know quite a lot. And one of the Swedish boiling water reactors, even the first one, had an isolation condenser. It's not working anymore, that plant, but still. There might be some manual. We are studying a little bit. Is there a manual possibility to close if the isolation doesn't work? And then we always have the containment to really close up everything if something was leaking even from the reactor circuit. I believe that things have to be basically quite simple. And it's nice if the team, especially the technical side, learns it from the top down, that how does this really work? Because then you know how important different parts of the plant are. We often forget that, and we put a lot of requirements on some single component or thing that is difficult to qualify, and we lose time, and we might lose the schedule in the project. And that's often a mistake. And in many modern projects, people don't see this big picture, and we use a lot of time on some single thing, although for the big context, it's actually not a headache, because nuclear safety is not built by relying on single components. It's actually built on a good systems architecture of the plant. What comes after this if this would fail? Even the containment couldn't sustain if the chain reaction went on going. And if there was a problem with the control rods, that they just don't go in. Not with hydraulic, not with the motor, there is a boron injection. So inject boron actually to the water of the reactor to shut down the reactor. That's not the normal that you use in boiling water reactors, you use that in the pressurized water reactors. But here is a backup system. So it's your last line of defense. And then on the right-hand side, we are studying what kind of features in the plant would help us to handle a situation where even the core would melt down, to really make sure that the containment still can sustain all those phenomena and things that are actually happening there inside the containment. This became quite usually, actually Sweden originally already in 1980 started preparing these kind of things after 3 Mile Island, and especially after Chernobyl, things were speeded up also in Finland and many other countries that we built dedicated systems. Here we are studying how that situation is handled. We know this reactor is a little bit smaller, but it's not a tiny reactor. It's still a considerable size, so we are studying that. We are very happy to see the development of the design that we have seen here. And here is a slide, so I just here kind of a disclaimer, not official stuff, still in the middle of the work. Very happy to see the development of the design. GE has done, and GE touched a lot to simplify things. We don't currently see any big headaches, but we are studying. We try to be critical because we are trying to make sure that also in our home market, Fermi, as the power company, would actually be able to also stand behind the design. And this is a pilot project. We look forward to actually using the same methodology for different designs. So this is our first pilot, but as Kalev explained, this is going first now, and let's see what other designs we might actually evaluate. Here are 6 things that we think are particular here, and of course GE knows that even better than us. The isolation of these bigger line breaks so that you don't have to really treat the large LOCA with the containment, for example, or the cooling system. How do you manage the small LOCAs where you're using passive systems for this isolation condenser and the containment cooling system? They come next. They are not really so novel things like this isolation condenser. It's about condensing steam, and that's not really new to us. But we are taking a look at how that is made really reliable. And there can be sometimes some devils in the details. It might be even in those that there are some isolation functions that if they are started inadvertently, without a reason, they might actually close those systems. You have to actually go, so I often say DID, defense in depth is also DID, devil in detail. So you have to go through certain things because we know the regulators will fundamentally also do that. So we are doing that now. Severe accident management, as I already mentioned. And then a huge thing here, autonomy of the plant. Not just this first situation after disturbance, operator doesn't have to do that, but how much time can we take without, for example, any external grid And here, the typical time nowadays is 72 hours, 3 days, but the designers have told us that they try to stretch it for a week, which is fantastic. We are also taking a look at things like how long the batteries will sustain. We don't need batteries to be safe, but we need batteries to be able to monitor the plant. And we also always have to remember that safety is a feeling based on facts. And the monitoring creates you some feeling, because you are not just so safety is a feeling based on facts. So risks are often very fact-based, but safety is a feeling based on facts. And that's why when we say that we want something to be highly unlikely with high confidence, this defense in depth is crucial, and also that we are studying all the possibilities there. And that we are also able to monitor the situation if we would end up in a difficult situation. This is what we are doing. Happy to answer any questions. Thank you.
Yes, so let's take a few questions. There's one question from the public. Maybe it's more to G. Hitachi, but let's see, maybe Timo can answer also. So it's more safety means more cost. Which one is BWRX-300 prioritizing? And there's an additional comment. Coffee example sounded like the coffee will be more costly than the house.
Yeah, of course, we didn't do the coffee solution that. Well, I guess we've heard so much from GE, so that is this design to cost principle. I also believe heavily having a very long safety background that these plants are still to produce energy. Safety is more that you really make sure and evaluate. First, you design something to do something good. Safety and risks is about evaluating, can I live with can I sustain certain situations? So I absolutely think this design to cost principle is good. That's the way to go. We've heard some other suppliers also. We know that to save the climate, we have to be with some sustainable price levels as well. So that's become even more important. First, you design it so that you get with reasonable costs, and then you actually evaluate the design to make sure that you have practically eliminated such consequences that you cannot live with. So I don't think I often say that safety and economy are the best friends. They are not enemies.
Good, thank you.
Because without economical things, you don't have money for maintenance. You are losing things. So safety and economy, or economy and safety, they go together. Mm-hmm. That's sustainable. We know that nowadays sustainability means actually people, planet, profit. So they are not enemies.
Yeah, good. Another question from the public. BWRX is only reference for Fermi, not the final chosen design. How much of the knowledge can be transferred to other SMR designs with other safety measures?
I don't fully, I have to admit, I don't fully understand the question, but I have to say something. So
I guess it's meant for our team, probably. Like you are doing the study now, and how easily you can imply this knowledge to other designs.
Very good, and I know that Martti Jeltsov, technical director, is pushing very much to actually engage the team. You don't learn much by listening to lectures, even this one. So you're only going to learn when you do something. So we are already talking with Martti that we will engage the Fermi technical team to actually evaluate this one and also the future, the other designs. So and we try to have this kind of a simple way of doing now, first with a very experienced team, but also engaging people from Fermi, that we, during this year, stepwise, we are getting a team that is not depending on any single individuals, and everybody starts seeing the forest, not just the trees. So that's the way we're going to go.
Thank you. I think we'll move on. Thank you, Timo.
Thank you.